Okay, so this video is about looking at dAdt equals 2 pi r dr dt, what that's all about, related rates, and I'd like to start with something that's familiar before we tackle the numerics and geometry of that. So we've worked with y equals 3x squared, and that intermediate step to getting a derivative, dy equals 6x dx. That should look familiar. We integrate with those terms, right? This small change in x times the geometry that's happening here gives us some nice relationships, a layering process, right? Now I can't show you 0.001. It's a small, but you know, it's kind of, the derivative here is how much ink am I putting down. If I had a small square, I'm not putting, let's say I'm changing by 0.001 the dimension, each time standardized 0.001, then the smaller the square, the smaller the change in area. The bigger the square, the bigger the change in area. And I think we can see squaring 2.001, we got familiar with this, I think, without a calculator. And this 0.001 is simply the cusp area of that layering process. And we can push that out to thousands of decimal places, so we ignore it. That's the major change. And if we look at this step, the change in y, 0.004 to 4 is 0.004. 2 times the x value, 2 times 2 is 4, times the change in x, 0.001, we can see that that works. And so we have captured a little bit of new area. And if we were to add those new layers of area, which are bigger and bigger each time, right, that's what integration is. And those are the two major concepts in calculus. That's more important that you understand that. That alone is more important than I can do the product rule correctly. Great. But it's all about understanding what the underpinnings are here that's most essential. So I'll erase this now. I think I can. Oh, and if I multiplied by 3 here, right? So I never did that yet. I just did the change in x, right? But if I multiplied by 3, then I would have gotten 12 and 12.0012. Okay, so that's 0.012. That would be the change in y for that function. And that is equal to 6x. We know how to take a derivative now. We're doing that enough. So 6 times 2 times 0.001. I should put that in parentheses probably. Okay, it's true. These relationships work. Okay, and this again is, okay, you got the area of a square. 6x dx is that layer. Okay, we can see it numerically work. Now what happens if I threw a pebble in a pond and I looked at it and I said, whoa, you know, these circles move away from where the rock, the pebble, hit the water. And let's say that I noticed that the radius, every second, the radius is changing by 2 units. Changing by 2 units. Well, where would the area be changing fastest? The biggest circle, in this case. And so I've decided to pick the number 3. And after 3 seconds, the radius is going to be 6. And I know the pi r squared gets me area. And so 6 squared gets me 36 pi. And I went to the calculator. I couldn't do that in my head. And I got 113.0973. And then I decided to try 3.001, just like we did over here. And I got 6.002. That's how long the radius is after 3.01 seconds. Changing at a 2-to-1 rate by the look. Yeah, 6 to 3, 4 to, yeah. And I put that in the calculator. And it was 36.024 pi, which I put on the top here as a decimal. If I multiply pi times 36.024, I got 113.1727. And 36 pi was 113.0973, and I'm just approximating. I just wanted to see the relationship with those numbers to see if they actually worked. And so I subtracted, because that's going to give me my change in area. Right here, that's going to give me my change. And I'm going to compare it to the change in time. Well, I know the change in time, still 0.001. Okay, and I can find this area. And it was 0.0754. If all my calculations are correct. I was doing it on an envelope in a restaurant. So Let's hope I didn't make any careless errors. Now, this would be more accurate if I had picked 2.999, right, and done those two numbers, because 3 is sandwiched between them, ham sandwiched. Maybe it should be vegetarian. The world should be moving towards being vegetarian. A fake ham sandwich with soy or something. And I shouldn't have gone off on that tangent because now I forgot where I was. Oh yeah, so the change in area, I just did the first 3 decimal places. This is a rough estimate, and I divided it by the change in time, 0.001. And I wanted to see if that actually came out to 2 times pi times the radius was 6. All right, that's where it was, radius 6. And dr dt, is 2 to 1. All right, so it's a 2 to 1 ratio. My radius is to time 2 to 1. And that came out to 75.398. Didn't surprise me that it was a little bit bigger. Actually, I was estimating everywhere here. So it seems to work. Seems like the numbers are working out. Now, I could have gotten more accuracy if I'd taken more time and picked a smaller change in time, sorry, 0.01. I think we're talking about limits here. All right, so what's happening over here? Well, what's the layering process? Well, I hope you can see that if I snippet this and open it up, right, then that is my dr right there. The width of the area that I cut through the circumference of the circle. Yes, the circumference of the circle is the layer, and if we give it a little bit of width, we got a rectangle here. All right, and that is going to get us our little change in area. Our little change in area, 2 pi r dr. But if our radius is also changing at a different rate, we have to account for that. And it looks like the numerics account for it. All right, so if your area is pi r squared, and you think of a as y and r as x, isn't pi pretty close to 3? Wouldn't you get the change in area without dt here? Wouldn't you get dA equals 2 pi r dr? And then wouldn't the change in area with respect to the radius equal 2 pi r? Which means that the bigger the circle, the more area accumulating around it with that circumference. Okay, so I hope that helps. I hope seeing the numbers play out gives you a little more confidence in the mechanics of taking some change and comparing it to time. All right. Hope the numbers speak louder than my attempt to explain it.